this technical session, as well as the competition that we are having, the e-Yantra robotics competition, in which there will be one of the themes in which you will learn a lot more about FPGAs. Um, so, so stay tuned. Hello, good morning all, and welcome to the technical session on Introduction to FPGAs. I hope I am audible and visible. So today's session on Introduction to FPGAs will be taken by our colleague Mr. Aditya Gudla, and the session is very important for the participants aspiring to compete in our competitions, including the Yantra robotics competition, in which we have one of the themes that will teach you a bit more details on FPGAs. So this session will give a flavor of what it would be to learn in that theme. And before we dive into the session, we have Professor Kavi Arya, PI of the e-Yantra project, joined with us. I request Kavi sir to address the participants and to start before we start the session.
Great, thank you, Vivek. I'd like to welcome you all to this morning's technical session. For those who don't know e-Yantra, e-Yantra is an outreach project funded by the Ministry of Education and hosted at IIT Bombay. It's been running for the last 11 years. This is our 11th year of existence. And to cut a long story short, what e-Yantra is trying to do is that we see a severe lacuna, a severe failing in our higher education system, as you all know, right? In the sense that a lot of the education is theoretical. And get out into the world, you are not very employable. In fact, NASSCOM reports and other reports show that up from 50 to 80% of the engineers who hit the world outside are unemployable, which is why companies like TCS and all that have extensive 6-month intense training programs to equip them with all the skills that they need to at least get started in the software engineering business. What eYantra has been trying to do is it's been trying to overcome this situation by directly reaching out to the students in the colleges. We've tried doing it through the colleges, through teachers and this and that, but we found that it doesn't work very effectively. While if we go directly to the recipients, to the beneficiaries, which is you students, we have amazing results. Like for instance, we teach you many complex engineering skills which are very contemporary and futuristic skills which you are not taught typically at the college. We teach you in the eYantra competition. So we've packaged all the gyan in the form of a competition which lasts over 6 months. And that competition has been known, has a reputation now, has a brand which is very desirable. Employers like it, students find it empowers them. Placements are on steroids, very good placements. Many students, as a result of this, are able to get positions in top postgraduate programs, both in India and abroad. Many of them spontaneously, after learning all the skills in the competition, are doing startups. We have a number of startups by eYantra alumni. So this session today is on programming FPGAs, which is just one of the elements which are taught in the eYantra competition. And remember, this is a very powerful concept. Programming FPGAs using Verilog and all that means that you're on the path to becoming a chip designer. Now, chip designers are very few and far between on the ground. This is going to be a skill which is going to be very much in demand in 2 to 3 years' time, because as the cost of hardware and reconfigurable hardware and the cost of chips and chip tooling comes down, there'll be a huge demand for these very high-end skills. And we are hoping that through the competition, you will be inspired to spend more of your undergraduate life learning things on your own, right? Taking off from eYantra, so that by the time you do your bachelor's project, your project is worthwhile, worth becoming a paper or potentially even a startup. So that is eYantra's dream, that as soon as we start engaging with you, students come in the first year, second year, third year, fourth year, everybody who comes and joins the community has gained a lot from it. So to give you a taste of one of the futuristic topics that we teach, we have my colleagues here. We have Vivek here, and we have Aditya Gudla, who is going to talk to you about programming FPGAs. So without much ado, I'll hand you over to our very talented team. So Vivek, over to you. And Ajit Harpude, as you can also see, who's here. Who else do we have from our team here?
We also have Gargi and Sachin sir handling the YouTube live stream.
Great.
Yeah.
So welcome all, and I hope you enjoy the session. And this is a taster for the kind of stuff you will encounter in the robotics competition. Take care. Jai Hind.
Thank you, sir, for setting the tone for the session. So now I request my colleague Aditya Gudla to start with the session. Meanwhile, there's a request for all the participants to kindly mute themselves unless they want to speak to the speaker or asked to do so. So yeah, so over to you, Aditya.
Yeah, okay. I hope I'm audible and visible also. So good morning, everyone. I'll be taking today's technical session on FPGA, Introduction to FPGA Design. So before we start this session, I would like to tell you all one thing, that let's keep this as a discussion rather than a boring presentation. So with that, I'll share my screen and start the presentation. Is my presentation visible?
Yes.
Okay, so I'll start with the presentation. One second. Okay. So in today's session, we will be discussing about FPGAs, what an FPGA is, the architecture of an FPGA, and then we'll discuss about the differences between an FPGA, a microprocessor, and an ASIC. Then we'll talk about basics of Verilog HDL. Then we'll look at a simple example of an ALU design, and we'll summarize our discussion.
To just interrupt here, I hope Vivek, this session is being recorded.
Yes, sir. This is being recorded and streamed live on YouTube.
Okay. Yeah, so firstly, I'll be starting with introduction to FPGAs. So before we learn about FPGAs, it is important to know what PLDs are. So a PLD is nothing but a programmable logic device. It is an electronic device which is used to build reconfigurable digital circuits. So you cannot build like analog circuits with PLDs. Only digital circuits are possible, and these digital circuits are reconfigurable, meaning that you can change their functionality as you wish. So when a PLD is manufactured, it has an undefined function. So if you give any input to a PLD, the output is not known. The output generated from a PLD cannot be predicted. Uh, 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 on the contrary, there are fixed logic devices. Like if you buy an adder circuit or a multiplexer circuit, when you give it some input, you know what output will be generated. So those are fixed logic devices, but PLDs are programmable devices, and they need to be configured for getting some sensible outputs from them. So when you configure a PLD, the interconnections between the logical elements are changed. So here is an example of a PLD. So this is a PAL. So here are the logical elements. There are some AND gates, some OR gates, some NOT gates. So when you configure this PLD, the connections between these logical elements are changed, and you define the output of a PLD by configuring the connections. So examples of PLD include PAL, which is programmable array logic, PLA, which is programmable logic array, CPLDs. CPLDs are complex programmable logic devices, and FPGAs. FPGAs, field programmable gate arrays. So I'll quickly talk about PAL and PLAs. So here you can see we have a PAL, which is programmable array logic. In programmable array logic, the inputs to the AND gates are configurable, meaning that we have a configurable AND gate array and we have fixed OR gate array. So here you can see that the inputs to OR gates are fixed. So these dots represent fixed connections. So output of this AND gate is connected to input of this OR gate, and it is a permanent connection. You cannot change these connections. And similarly, this OR gate is connected to output of this AND gate and output of this AND gate. So, but input of these AND gates are configurable. So here you can see that the input of this AND gate is connected to X and it is connected to Y. But and this AND gate is connected with inputs X and Z bar. So based on these connections, the outputs A and B will be generated. But let's say if you want to generate some different outputs, you need to configure these connections and you will be generating different outputs. Next, we have a PLA. PLAs are nothing but programmable logic arrays. And here you have configurable AND arrays and configurable OR arrays. So here you can see that the inputs to AND gates is configurable and inputs to OR gate is also configurable. So based on the configuration, you can generate some output based on the inputs X, Y, and Z. Okay, so any doubts, Prino? If you have any doubts, you can unmute and ask. Okay, so I'll move on. So next we have FPGAs. So FPGAs are nothing but programmable logic devices, uh, and uh, and they contain an array of logic elements. And there are different names for these logic elements. Logic elements are also called as logic blocks or configurable logic blocks. And the field programmable means that the FPGA device is configured in the field. That is, it is configured by the user and not the manufacturer. And as I said, these FPGA devices contain logic blocks. These logic blocks are interconnected with each other with the help of programmable interconnects. And these interconnects between the logic blocks define the functionality of an FPGA. So if you want to implement some application on FPGA, you define the function of a different logic blocks, and these different logic blocks are interconnected with each other to generate the final output. So a logic block is like the heart of an FPGA, and it contains some elements like a lookup table, some storage elements like flip-flops or registers or multiplexers. And the elements, the exact elements inside a logic block depends on the manufacturer or model of an FPGA which you are using. So yeah, and an FPGA also contains I/O blocks, and these I/O blocks basically help to communicate with the logic blocks from the external sources. So if you have some switches, some LEDs which you want to drive, or any input-output devices, you can connect them to an FPGA with the help of I/O blocks. So this is the architecture of an FPGA. So here you can see there are many logic blocks. So these blue blocks are the logic blocks. So as I said, logic blocks will contain some lookup tables, some registers, some multiplexers, and yeah, these exact elements depend from manufacturer to manufacturer and the model of an FPGA. So yeah, based on your application, these logic blocks will be configured and they will be interconnected with each other. Next, we have programmable interconnects. So as I've said, the logic blocks are interconnected to each other with the help of programmable interconnects. So let's say if you want to connect the output of this logic block to output of this logic block, they will be routed accordingly with the help of the programmable interconnects, and the appropriate action will be performed and output will be generated. And the last element is the I/O blocks. So I/O blocks help with the communication with the external devices. So either you can input to the FPGA or you can output from the FPGA. So these blocks help with that. And some FPGAs have specialized hardware like block RAMs or DSP units or multipliers. So that is specific to that particular FPGA. Okay, so any doubts with the FPGA architecture or previous slides? So yeah, so a quick summary. So basically, FPGAs contain many logic blocks, array of logic blocks, and these logic blocks are interconnected with programmable interconnects to achieve some output. And there are also I/O blocks which help to interface with the external devices. So these are the major elements of an FPGA: programmable interconnects, logic blocks, and I/O blocks. Next, we have FPGA design flow. So here are the steps involved in an FPGA design process. So whenever you design an FPGA application, like if you want to, let's say, design a counter or design a, let's say, a logic function of 32-bit input or anything like that. So you basically use FPGA design tools like Cortex or Vivado. And when you do that, you basically don't really bother about what logic elements are there, how many logic elements are there, how are they interconnected. That all is handled by the design tool. You just need to make sure that whatever application you are working with, you have enough logic elements so that your application can be implemented on that particular FPGA. So you need to only worry about that. The rest all will be taken care by the design tool. So yeah, firstly, in the design process, we have design entry. So here you, uh, anyone has any doubt? Okay, so first step is the design entry. So here you define the algorithm or define the output which you want to achieve. So basically, this is your HDL code. It can be a Verilog code or VHDL code. Based on your code, circuit will be synthesized. So here you can see that this is my Verilog HDL code, and based on this code, I'm synthesizing some output, synthesizing some circuit. So here this code is for a full adder circuit. So in full adder we have input A, input B, and Cin, and we have some output and carry out. So this is the synthesized circuit which the FPGA design tool has synthesized. And in the next step, we are supposed to implement this circuit. So in the implementation step, the synthesized circuit is implemented on the FPGA architecture. So in the FPGA architecture, we only have logic blocks which have limited functionality. So based on your final synthesized circuits, these logic blocks are configured, and maybe one or more logic blocks are used, and they are configured differently for different output, and they are interconnected with each other to generate the final output. For example, we have some AND gates, some OR gates, and some XOR gates in our synthesized circuit. Let's say our this logic block is used to generate the output of an AND gate. This logic block is used to generate the output of an XOR gate. This logic block is used to generate output of an OR gate. So these blocks are configured accordingly, and then they will be interconnected so that you get the final result. But that is not the case, because these logic blocks can like act as a full adder by themselves. So maybe only one logic block is used, but I gave you an example just so that you understand like how logic blocks are configured. So yeah, so these logic blocks have limited functionality, and depending on your application, they will be configured and they will be interconnected. Okay. Then after the implementation step, a bitstream file is generated. So all these steps are involved with the design tool and not on the actual FPGA hardware. So the design tool basically performs the synthesis process, and then it implements it, and it generates a bitstream file. So this bitstream file contains the information about the configuration of logic blocks, configuration of the IO blocks, and the interconnects between them. So this bitstream file is then uploaded to the FPGA, and then the FPGA basically implements the final design. So any doubts till now? And also we basically perform simulation while we are synthesizing and implementing our circuit. So basically when we write our HDL code, we basically simulate it and we check for its functionality, which we verify its functionality if it is correct or wrong, and if there are any errors or if there are any bugs, we resolve them here itself. And then we'll synthesize the circuit, and after a circuit is synthesized, we again verify if the synthesized circuit is able to perform the desired function or not. And after synthesis, we'll again implement the synthesized circuit on the FPGA, and then we'll again perform the simulation, and we'll check if the implemented circuit is able to perform the desired function or not. So firstly, we perform pre-synthesis simulation, then post-synthesis simulation, then gate level simulation. Okay, so any doubts or any points to discuss? Okay, so I'll move to the next slide then. Yeah, so this is an example of how synthesis happens. So you basically write an HDL code. So this is an example of a full adder. And based on your HDL code, a circuit is synthesized. And this circuit is synthesized and then implemented on the FPGA. So now I'll talk about differences between FPGA microprocessor and an ASIC. So yeah, firstly, I'll talk about full custom design and semi-custom design. So whenever an IC or a chip is manufactured, there are majorly two design styles. One is full custom design style, wherein the IC or chip is designed as per the application, and it is basically customized at the transistor level. So you basically choose which transistor to put, how to interlink them, and how to optimize for the area, how to optimize for the performance. All the control you can have, because you are basically customizing the entire design. But by doing so, you basically incur a lot of cost, because this design technique is very costly, because there is a lot of
Hello, can I ask? I have a small query.
Yes, sir.
what is the difference between design and synthesis? Because yeah, that I just wanted to know. Like it seems very similar. Like what is the difference between design and synthesis?
So, sir, this is the design entry. So, design entry means that you give it some input. So, let's say I can give it some Verilog code or some HDL code, and based on that code, it will synthesize some circuit. So, synthesis is basically generating a circuit. Design is basically a code. Design entry is code, and synthesis is the circuit of that code.
Okay, fine.
Yeah. Okay, so yeah, so I was talking about full custom design. So I said it is a costly design technique, and its time to market is quite high because you are basically doing everything from scratch and you're optimizing all the things all by yourself, and you're customizing for that one particular application. So time to market is very high, and the example of uh, full custom design technique is an application specific IC. So an ASIC is basically a circuit or an IC designed for any one particular application. Let's say if you want to design a chip which goes on a satellite, so that becomes an ASIC. It basically performs a very specific application, and in those particular applications you need very high performance, very low power consumption, and so you cannot afford to use like general purpose processors or anything like that. You basically need very optimized hardware for that. So in that particular case you will use ASICs. So next we have semi-custom design style. In semi-custom design style, we basically use standard library components to design the final circuit, final IC. So for example, if for designing a full adder, we can use a half adder circuit, which is already designed and which is already optimized properly, which takes very less area. So we can use such designs to create like a final design. So basically, this technique is cheaper than full custom design technique because it reuses a lot of things. It reuses a lot of design libraries which are already built and which are already optimized. And time to market of such designed ICs is less compared to full custom designs because of the reuse of resources. And uh, and one particular and if you design an application in FPGA, that can be considered, it is not like a full custom design, but it can be considered as an semi-custom design application. So if you design an FPGA application, you basically have all the hardware, but you configure that hardware based on your application. So that can be thought of as a semi-custom design approach. And also the microprocessors nowadays, basically they use processing cores from vendors like let's say the Snapdragon processor, which is present on our phones. They use like processing cores from ARM Cortex. So that can be also interpreted as a semi-custom design technique. Okay, so I'll move on. Yeah, so next is the difference in the operation of these devices. So as I said, in an FPGA, the operation is basically based on the configuration between the logic blocks, how they are configured and how they are connected. But inside a processor or a microprocessor or a microcontroller, uh, these devices have a fixed hardware. So there is some. This is a very simplified architecture of a microprocessor. So it has some ALU, some control unit. It has some memory and some IO devices. So when you write a code, let's say if I want to perform B plus C and assign that value to A, and if I want to perform E plus F and assign that value to D. So basically, this code is converted to multiple instructions because this particular code, a line of code consists of, like, let's say addition. Then addition, the result of addition is moved to a variable A. So there are many instructions involved. So these instructions are executed sequentially one by one inside a microprocessor. and then the final output is computed. If I write two statements like A equals to B plus C and D equals to E plus F, these two instructions or these two lines of code are executed one after the other. But inside an FPGA, if I want to execute them parallelly, what I'll do is I'll basically I'll configure some logic blocks to perform this action and configure some logic blocks to perform this action, and they can run independently. So basically that is the main advantage of using an FPGA. So FPGAs can basically achieve parallel operation, which microprocessors or microcontrollers cannot achieve. So that is a very huge advantage of using an FPGA. So this is a very simple example where only addition is performed, but FPGAs can handle like hundreds of parallel tasks where a microprocessor can do only one task at a time. So that is the main difference. And of course, in ASIC, the operation is basically dependent on the design. So the way you design an ASIC defines the mode of operation of an ASIC. It can basically have serial operation or a parallel operation. Basically depends on the design of an ASIC. So any doubts till now? If anyone has any doubts, they can unmute and ask. Okay, so I'll move on to the next slide then. So to summarize, basically using a microprocessor or a microcontroller, we cannot achieve like very high performance. So performance is low, but the cost is really low. Like we get microprocessors or microcontrollers for like few hundreds of rupees, and time to market is also very low because you already have the hardware ready. You only need to program it, connect some peripherals, and then you can design your application. So time to market is very low. In an FPGA, performance is moderate. Of course, these numbers are like not the absolute numbers, because if you buy a very high-end processor and a low-end FPGA, performance of that particular processor will be high, of course. But in general, these numbers, these entries in the table are good. So performance in an FPGA is like moderate compared to a microprocessor and an FPGA, and cost is also moderate, and time to market is also very low because you already have the hardware. You just need to configure your FPGA device, connect some external devices to it, and then you are ready with your application. So time to market is also very low for FPGA. In ASIC, you get very high performance. You can basically optimize all the parameters as per the application. So very high performance is achieved. Cost is, of course, very high because everything is designed by you. Time to market is also very high because everything is custom designed for that one particular application. Okay, so next we'll talk about Verilog HDL basics. But before that, any doubts till now or any suggestions, comments?
Hello, sir.
Yeah.
Sir, SoC design falls under which category? Does it come under?
So basically, SoC design, in SoC design, no one designs it from scratch. So as I mentioned that if you talk about any SoC, you like let's say if there is a Qualcomm Snapdragon SoC which is used in our phones, so that SoC will basically have a processor, a GPU, and many other components. So they don't basically design everything on their own. So they'll basically buy IPs from different vendors, and they'll integrate them. So basically that also falls under semi-custom design only.
Okay, sir. Fine. Thank you.
Okay, so any more doubts?
Sir.
Yeah.
Sir, FPGA, we have generic boards. In ASIC, we have generic boards, or they are self-designed boards only available?
No, ASICs basically you design them all by yourself based on your one specific application. So let's say if you want,
they cannot be reprogrammed for any other task.
You can design a reprogrammable ASIC also. So ASIC is basically, you can design it anyway based on your application. So if you, let's say, if you want to design an FPGA which has with built-in processor, with built-in RAM and all that, so then that design becomes an ASIC. So,
Okay.
so
If the basis 3 board is the generic FPGA,
okay,
so if you modify that basis 3 board, then it will be converted to an ASIC.
yeah, but yeah, yeah. If you modify that, and if you basically uh, change the internals and change the behavior of that based on your specific application, then it basically is an ASIC. Okay, so next we will talk about Verilog HDL basics. Yeah, so in today's presentation, I won't be covering a lot of details about Verilog HDL because there are a lot of things to cover in Verilog itself, and that is not possible in this short session. So I highly recommend you all to like visit these links. So first link is a PDF from Altera. So if you type Verilog HDL basics, you will be able to find this PDF. It is a very short 20-page PDF, I think, and it covers a lot of things. And next is a YouTube link from Intel, and that also covers a lot of things in detail. So I highly recommend you all to go to these links and study more about Verilog. So yeah, firstly, what is HDL? So HDL is basically hardware description language. So it is a programming language which is used to model a piece of hardware. So we saw previously that writing a Verilog code generates some hardware. So basically, Verilog code is an HDL which models a piece of hardware. That hardware in the previous example was a full adder. So there are two popular HDL languages, which is VHDL and Verilog. So VHDL stands for Very High Speed Integrated Circuit Hardware Description Language, and Verilog stands for Verification and Logic. So these are the two popular HDL languages. Today we'll be talking about Verilog. This is the Verilog code structure. So every Verilog code starts with the keyword module and ends with the keyword end module. So basically, a module can be thought of as a component, or like let's say in simpler words, it can be thought of as an IC. So so it can be a full adder IC, it can be a multiplexer IC, and you can give any name to your IC. So let's say if I give it a name of full adder, so it becomes my full adder IC. And every IC or every component will have some pins, right? So so you define those pins in the port list section. So here you define all the pins which your module has or your IC has, and then you declare those ports. You either declare them as inputs or you declare them as outputs. So here you can see that A, B, C in, sum, C out. These are the ports of my component, and A, B, and C in are the inputs. Sum and C out are the outputs. So this is the port declaration section. Then we define data types. So here we define X, Y, and Z as wire. So I'll come to data types a little later. So this is the
Aditya,
yeah.
sorry to interrupt. Could you paste that link probably in the chat?
I'll do that one second.
Okay. Yeah.
Okay, someone has raised hand, so you can unmute and ask. Vivek, so I've shared those links in chat, so I think they should be visible to you. Okay, so should I continue with?
Yes. Yes.
Yes.
Okay. So yeah, so uh, wire is a data type, and I'll come to data types a little later. And in this module, you define basically the functionality of that particular module. So if it is a full adder module, you define how that full adder is functioning and how inputs and outputs are interlinked with each other. So you define the functionality of that module, and then the keyword end module, which ends the module. So here is an example of a Verilog code, which is a simple code of a full adder. So we start with a keyword module and we end with keyword end module, and we define the module name. So in this particular case, module name is full adder, and here are the ports of this module. So A, B, C in sum, and C out. So A, B, and C in our inputs, sum and C out are outputs. And we define variable data type, which is a wire, X, Y, Z. These three are wires of same data type. Then we define the functionality. So here we are defining that we are defining it in a different way. So I'll come to this how this is defined a little later. So here you can see that we are using two half adders. So basically, full adder is nothing but a combination of two half adders. So first half adder calculates sum between A and B, and the second adder calculates sum between the sum and the C in. So that is defined. So here you can see that A and B is input to this particular half adder one, and it is generating some sum, and that is outputted on the wire X, and it is generating some carry, and it is outputted on wire Y. So X and Y are defined here. And later in half adder 2, X is summed with Cn, and it is generating the final sum, and it is also generating some carry, which is outputted on Z. And finally, the final C out is basically OR between Y and Z. So this is basically the functionality of our full adder module. So yeah, next I'll talk about the modeling styles in Verilog HDL. So first modeling style is basically behavioral modeling. In behavioral modeling, you only define the functionality. You don't follow any structure in the code. You basically define how variables, how inputs and how outputs are interlinked with the help of if statements, case statements, if else, while loops, for loops, all those operators. And in this particular modeling style, synthesis circuit is difficult to predict. You cannot guess what circuit will be synthesized in this particular style of modeling. So if I say if flag is 1, A should be so and so, count should be so and so, else A should be E, count should be decremented. So if I look at this particular code, I'm not able to figure out like what hardware is synthesized if I write this particular code. But it is very easy for us to understand like what is happening in the code and how variables are updated. For us, it is very easy, but it is very difficult to guess the synthesis circuit. In next modeling style, we have structural modeling. So in structural modeling, we define the functionality structurally. So in previous example also, we used structural modeling and some other modeling style. But so here you can see we have instantiated some modules. So this is basically structural modeling style. So basically you define the behavior of the circuit in terms of components, like how inputs and outputs are interlinked and how they are operated on components. So that is how you define the behavior in structural modeling style. So yeah, so you basically use components and instantiate them in your code to define the functionality in structural style of modeling. In data flow modeling, basically hardware is defined in terms of flow of data from input to output. So here you can see input and output are operated using this AND operator, and it is outputted on the output one. So it basically tells you how inputs and outputs are interlinked using the assign statements. So it is very simple to understand. But again, synthesis circuit cannot be predicted. So in the first case, like output one is basically AND between input one and input two. So this is easy to understand because it is only one particular operator, and we can guess that AND gate will be synthesized for this particular line. But in this particular line, we cannot say like it is not very obvious like what hardware is synthesized. So so uh, it is basically that you basically define the relation between input and outputs in data flow modeling using assign statements. Next, I'll talk about data types. So before data types, any doubts till now or any comments? Uh, if you have any doubts, you can unmute because I'm not able to see the chat.
Can you tell about structural modeling once again?
Okay. Yeah, so in structural modeling, you basically define the structure. So let's say if you are defining a full adder circuit. So as I said, a full adder will basically is basically composed of two half adders, right? Two half adders which are cascaded. So in structural style of modeling, you basically do that. So here also you can see that we are using two half adders. So half adder one and half adder two, and basically they are cascaded by connecting appropriate wires to the appropriate inputs and outputs. So that is how you define the hardware in structural style of modeling. Uh, any did I clear your doubt or you have any more doubt?
Yes, thank you.
Okay. Okay, so next I'll talk about data types. So there are basically two major data types in Verilog. First is a net data type. So a net basically defines physical interconnection between components. So basically in this particular example, we are using X, Y, and Z. So X is basically a connection between half adder 1 and half adder 2. So here you can see that X is common to half adder 1 and half adder 2. So basically this is a net. But similarly, same case is with Y and Z. Z is common between this half adder 2 and the C out. So 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 basically, a net represents interconnection between components. And the variable, and next we have variable data type. Variable data type represents some storage element. So if I define a reg, it will basically be defined as a register. So which can store some data in it. Uh, I'll come to these. So in net data type, we have basically three subtypes. So first is the wire. So wire is basically a node or a connection, as I mentioned just now. And a trie is basically a tri-state node, which can have three particular values, either a 1, a 0, or high impedance state. And next we have supply 0, which is logic 0, and supply 1, which is logic 1. And in variable data type, we have reg. Reg is basically an unsigned variable of any number of bits. So you can define a reg with any number of bits. So here you can see that we have defined reg q, which is of 16 bits. So this is basically a bus. You define a bus in this particular way. And we have an integer variable. So integer can have 32-bit signed number, and real time and real time are also variable data types, but they are not synthesizable. So not synthesizable means that hardware cannot be synthesized by using these particular data types. So these particular data types are only used for simulation and not used for synthesis and for actual implementation. So any doubts with the data types?
Hello, sir.
Yeah.
Sir, is the tri-state node synthesizable?
Yeah, it is synthesizable. Tri-state node is synthesizable.
Okay, sir.
So Verilog supports high, low, and high impedance state also.
Okay, sir. Thank you.
Okay.
Sir.
Yeah.
So that wire is a dummy node, no, which we are creating. So that we will not get in that RTL view.
It is not a dummy node. So basically, if you go back to this circuit, so the output of this particular XOR gate, so this node number 3, so that is basically a wire. So this is the node, and this is a wire, and it is actually a physical wire which connects the two components. It is not a
Okay.
dummy node.
In try, what will happen?
In try, basically, the output is basically comes. The output can basically have three particular values. So it can either be 0, it can either be 1, or it can be in high impedance state. So that is a try node.
So high means it is not a digital logic.
High is basically digital, right? High and low are digital logic. High impedance means it is not connected to anything. It basically offers very high impedance, so it is basically not connected to anything. That is the meaning of high impedance state.
Okay.
So any more doubts, or should I move on?
These wires, try and supply, everything would be there in that RTL view. Nothing is like dummy we are creating just to connect a node from here to there.
No. These are the actual nodes, not the dummy nodes. Okay, so I'll move on to the next slide then. So next we have continuous assign statements. So basically, in using continuous assign statements, you model the behavior of a combinational logic using some expressions and operators. So here is an example. So this is a continuous assign statement. So output is assigned value of A and with B. So this is a continuous assign statement which is used in data flow style of modeling. So assign keyword is used, and some based on some expression output is evaluated. And in this particular case, LHS must be a net data type. So output is basically a wire, and it is always active, meaning that output always has some value based on input A and B. It cannot be don't care or any other value, because it is always assigned to some value which is dependent on A or B. And RHS can be a net, meaning it can be a wire or a try or anything like that. It can be a register or a function call. So continuous assign statements are basically used in behavioral style of, a data flow style of modeling. Next, we have procedural assign statements. So there are two procedural assignment statement blocks. So first is the initial block, which is used to initialize the behavioral statements. So if you have any variables, if you have any registers or anything like that, you can basically initialize them to a default value using initial block. So that is the use case of initial block. And next,
I have one query, sir.
yeah.
So like the different behavior, like behavior modeling, structural modeling, they can be present in a single program. No? Like we can have
Yes.
different way of modeling
Yes.
into a single program. Is it possible?
Yes, sir. Yes, sir. Basically, we never use any one particular style of modeling style because it is very difficult to follow only one particular style. We basically use a combination of two or more of those styles. So even in this particular example, you can see that uh, half adder 1 and half adder 2 are instantiation of some modules. So this is basically a structural style of modeling. And then we are using some assign statement. So this is basically data flow style of modeling. So we basically use a combination of different modeling styles. It is not only one particular style.
And one more thing, while declaration, when you use wire and variable like this, so do you also specify type there, or you just say wire?
Wire is a data type, sir. So
Okay.
wire comes under a net data type. So net basically it is inferred that it is a net. So you need not say it is a net or variable. So wire is a net data type. You only need to say wire. That's it, and the names of that wire.
Okay, fine, fine.
Excuse me, sir.
Yeah.
In VHDL, we used to mention the library or name of the library from which
Yeah.
the wire or the terms are coming. So in Verilog, we have to not mention the library.
No. In Verilog, there is no need to mention any particular libraries or anything like that. It is already present in the. It is basically inferred in Verilog what libraries to use.
And one more doubt, sir. Cortex cannot be used for programming FPGAs.
It is used actually. So basically, in Cortex you can
I
design
had,
your
I had,
application.
I had, I had, I had used that for CPLD boards,
Okay.
but for FPGA, I don't have any idea.
So basically, in the theme which we are having in EYRC, so even there we are using Cortex to program our FPGA boards. So basically, I think there is an option to program device under tools, I think. So there you can upload code to your FPGA board.
Okay, so the Digiland board which Vivado has made, so then that cannot be used in Cortex, no, but
No, that cannot be used because the Cortex tool is manufactured by Intel, and that tool only
okay,
supports
Intel
Intel-based
devices.
boards. Yeah,
Okay, sir, but both the languages and all the types of the modeling can be used for programming our CPLD and FPGA boards.
I'm not very sure about CPLDs because I've personally never used CPLDs, but yeah, for FPGAs, whether it is Intel-based
So
FPGA or
we can
Xi,
use VHDL language for programming FPGAs.
yes, you can.
And the style of modeling which we are comfortable, we can use that because the end output is the important thing.
Yeah, any style of modeling you can use based on.
Any combination or any style.
Yeah. You can use only one particular style or maybe combination of two
So
or three.
in the competition, we are not using Xilinx, Vivado or anything. We're using Cortex only.
Yes, we are using Intel-based boards and we'll be using Cortex tool.
Okay. So the kits of that we are having in that eLSI lab, which will be programmable using Cortex.
I think your eLSI lab should have Intel boards, D0 boards, but you
Oh,
need to check with your college, I think.
okay, sir. Okay, sir. Thank you.
Okay. Okay. So I think yeah. So I think I talked about procedural assign. I was on this particular slide, I think. So procedural assign statements basically consist of two main blocks. Initial block, I said, is used to initialize all the registers, all the variables, and all. Always block is used to define the functionality of behavioral statements. So in behavioral style of modeling, so wherein you define behavior using if statements, for statements, case statements. So this particular piece of code has to be written inside an always block. So basically, always blocks are used in basically behavioral style of modeling. So 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 that is the use case of always block. And always block and initial block represent a separate process. So these processes run in parallel. So if you have multiple always block, let's say if one always block is used to compute a plus b, next always block can be used to compute a minus b, anything like that. So previously I had mentioned that in an FPGA you can achieve parallel operations. So if you have multiple always blocks, and if those blocks are independent of each other, then you can have any number of always blocks which can do computations parallelly. And yeah, statements inside these always blocks are run sequentially. So in this particular example, if you have this piece of code inside an always block. So this code has to be executed sequentially. Otherwise, you won't be able to get the correct output. So first flag is checked, and if flag is 1, then only the contents inside of that if block are executed. Otherwise, else block is executed. So in contents inside an always block are always executed sequentially, but the individual always blocks are always executed parallelly. So that is the meaning of this statement, that each always block and initial block represent separate processes, and these processes basically run in parallel, and statements inside these process blocks execute sequentially. So that is about procedural assignment statements. So any doubts with continuous and procedural assignment statements? Okay, then finally I'll move on with this example. So this is a very simple ALU design example. So here is the code. So this ALU basically performs 4 operations. Addition operation. So here you can see we have addition operation. Then we have subtraction operation. Then we have multiplication. Then we have logical NAND operation. So this particular ALU is designed to perform these four operations. And so yeah, as I mentioned, any piece of Verilog code starts with module and it ends with keyword and module. And this is the name of the module, so which is ALU, and this is the port list. So in Verilog, we also have the option to combine port declaration in the module itself. So here we have defined the port list, and we have also defined the functionality of that port. So A is defined, B is defined, and it is also defined that these two are inputs. And ALU select is also an input, which is of 2 bits, and A and B are of 8 bits. So this is an 8-bit ALU, of course. And we finally have an output, which is of 8 bits. We are defining a data type called reg, which is a variable data type, which is of 8 bits, which is used to temporarily store the result of an ALU. And the final result of an ALU is assigned with this value. So here you can see that the assign statement is used, and the final output, which is this output, is assigned the value which is similar to this reg. So whatever value this particular reg will have, that value will be assigned to ALU out. So this particular style is the data flow style. And this particular style of modeling is the behavioral style of modeling. So here we are using an always block, and here we are mentioning that always at star. So basically this is the sensitivity list. So always blocks are sensitive to some events. So you can have, let's say, like always at positive edge of clock. So this always block will be executed only when there is a positive edge of clock. So this is the sensitivity list. Or we can say we can have always at A. So whenever A changes, the always block will be executed. But for our case, we want our always block to be sensitive to all particular conditions. So whenever A changes, whenever ALU result changes, this always block should be executed. So whenever you mention star inside these brackets, so that means that this is a combinational logic. And if you know that an ALU is basically a combinational circuit, so that is why we are modeling a combinational type of logic for our ALU. So always at star, then we are beginning the always block by begin keyword, and we are ending that always block by end keyword, and then we are defining a case statement. So this case is sensitive to the ALU select. So the ALU select can have 4 values, 0, 0, 0, 1, 1, 0, or 1, 1. So based on these 4 values, addition, subtraction, multiplication, or logical NAND will be performed. And we have default.
Sir, I have one query.
Yeah.
So what is the difference between output that you defined there, 0 to 7, 0:7, and assign out ALU out?
So these particular statements, sir.
Yeah. You have defined output 7:0 ALU out, and then you have also defined ALU out in the next block.
So these this statement and this statement you're talking about.
Yes.
Okay, so this is basically defining that ALU underscore out is my output, right? So this is the port of a module. So this particular port is an output port that is defined by this particular line. I think that should be clear.
Yes.
But the value of this particular output has to be defined somewhere, right? So what value this particular output have? So that has to be defined. So that is defined here. It says that this particular output will have the output which is similar to ALU result. So whatever ALU result variable has, so that particular value is assigned to my output.
Okay. Fine.
Then basically what we'll do is we'll basically change this ALU result, which is a variable data type. So when you use assign statement, assign statements can have only one particular value. So that is this particular value, ALU result. But a variable data type can take many values. So here you can see that ALU result can take a plus b, a minus b, a multiplied by b, or n.
Okay, fine. So for assign statement, I can assign some statement, and then that would be reflected to output.
Yes. So yeah, now inside the case statement, we are basically defining the behavior of the ALU result. So if select is 0, 0, then ALU result will be A addition with B.
Robotics competition, in which there will be one of the themes in which you will learn a lot more.
Okay, so yeah, 0, 0 ALU result will be A plus B. For 0, 1 A minus B. For 1, 0 A multiplied by B, and 1, 1 it will be logical AND. So any doubts with this code, or should I move on with the simulation result?
Sir.
Yeah.
Hello. Yeah. Can you please explain once more that the part of where that always positive age that one?
Yeah, so basically always blocks are sensitive to some particular events, right? So if I write always at positive edge of clock, so whenever there is a positive edge on the clock input, then this always block will be executed, else it will be not executed. So if I have, let's say, constant 1 or constant 0 clock, then clock as in some particular value on the clock signal, then this particular always block will not be executed. It will not compute any ALU result. Whenever there is a positive edge, only then this always block will be executed. So this part is clear.
Yeah. Okay, sir. Thank you, sir.
So that is basically sensitivity list. So for our particular case, ALU is basically a combinational circuit. It is not sensitive to it is always sensitive to its input. So if I write star, that means it is sensitive to A, it is sensitive to B, and it is also sensitive to ALU select. So whatever variables are present inside this particular always block, it is always sensitive to those. So that is the meaning of this star. It means it is sensitive to all the values, all the values. So whenever there is change in any one particular value, it is executed. This always block is executed.
Sir,
Yeah.
sir, actually in the logic of multiplication, it as it is a process of addition, so the synthesis process will be sequential circuit or it will generate a combination circuit?
For multiplication.
Yes, sir.
For multiplication, in this particular case, it will generate a combinational circuit because we are not defining any clock. We are not we are not saying like how multiplication is happening. So the simplest case would be to synthesize a combinational circuit. If
Yes.
let's say if I define always at positive edge of clock, then I say that multiply only one bit at a time, then it will define a sequential multiplier.
Okay, sir.
But in this particular case, it will synthesize a combinational multiplier. Okay, then I think let's move on to the simulation results. So this is the simulation which is performed in Quartus only. So here we have inputs A and B, and we have select line. Select line basically can take four values 0, 0, 0, 1, 1, 0, and 1, 1. And based on that, ALU output is computed. So in the first particular case, ALU select is 1, 1. A 1, 1 basically corresponds to NAND operation between A and B. So if you perform NAND operation between A and B, you will get this particular result. So 0, 1 NAND is 1. 0, 0 NAND is 1. So you can verify all the bits if you like. And next case, we have 1, 0. 1, 0 is basically, I think, multiplication. So if you multiply these two numbers, you will get this particular output. So let's consider one simple example of addition. So here is one number and here is another number. So 1 plus 1 is 0 carry 1. I think that everyone knows. And 1 plus 1 plus 1, because we had one carry, so that should be 1 and carry 1. So if you do the addition of these two numbers, then you should be able to get this final result. Again, similarly, we have 1, 0 case, which is subtraction of these two numbers. Okay, so any doubts in this? I'm done with my presentation, so if you have any doubts, we can discuss.
You've done an excellent job, I must say.
Thank you, sir.
Okay, so I think he's left himself open here for questions. So if there's anybody here, please do open up. But let me share with you what Aditya has presented to you is a very electrical engineering oriented picture of circuits, right? So he's speaking from the point of view of an electrical engineer who wants to make it easier to build circuits. But the future, I feel, is going to belong less to the electrical engineers and more to the software engineers. Now, let me explain to you what I mean by that. Okay, so to program FPGAs, to program circuits at the moment, to build chips and stuff like that, one needs languages such as Verilog and VHDL, which are essentially high-level modeling languages for behavioral modeling and structural modeling and data flow modeling. But at the same, so you're essentially thinking at a very low level of abstraction. You're thinking still in terms of circuits and all that, okay? But the world has moved on into very interesting spaces, which is why we are very interested in things like programming FPGAs. A PhD student of mine a few years ago did some work where he took a C program, and this was co-guided by Professor Madhav Desai, who's the inventor of the Ajit chip, the Ajit processor in IIT Bombay. Samir Sasrabuddhe was his name, and he came up with a compiler which could take C code and compile it to an FPGA. Now, isn't that mind-blowing? What that means is that to create a chip, I don't need an electrical engineer or a microelectronics engineer anymore. I need a software programmer. But software programmers don't really know how to play with hardware, because designing software code is distinct from hardware code, where you got to be very careful about resources and stuff like that. Okay, so he came up with a paradigm and he called that AHIR, a hardware intermediate representation. And AHIR was used as the basis for designing the Ajit, the processor. But the only reason I'm saying this is that don't think that FPGAs are meant only for electrical engineers. FPGAs are meant for everybody who wants to convert an algorithm into something that runs really fast. Now, processors are a fossil basically, in the sense that it forces a sequential processing on you, and it's very power intensive, right? So if you want to do video processing and stuff like that, it is very inefficient doing it in von Neumann processors, which are step by step single thread of instructions. Very inefficient doing it in the conventional processors. But if you do it in specially designed hardware like GPUs, and if you like going directly to the electronics itself, it's much more efficient. So this whole space is very interesting of hardware, software, co-design. There's a lot of interesting and exciting work happening in this area. At the moment, designing a new chip costs a lot of money. Like for instance, the Apple series chips, just the tooling for that costs billions of dollars. Billions, okay? So nobody wants to build new chips that easily, but there's new technology which is coming on the horizon. First of all, that is 5 nanometer technology. Now, if you go to 180 nanometer technology, for which we do have the fabs in India, the cost dramatically comes down, right? And nowadays they are talking about printable circuits on flexible ICs and stuff like that. So this is a very exciting area. So what used to look like a microelectronics engineering problem in the past is soon going to be a software engineering problem. And I think the time is very soon where you can write Python code and just compile it into hardware to run on an FPGA, or even maybe build a chip out of it. So I just wanted to tell you that nothing is really cast in stone. Science is creating amazing breakthroughs at the moment in this entire space of reconfigurable hardware and low cost chip design. And these are very valuable and important skills that you should consider acquiring as we go along. Aditya, what do you react to this? What do you say?
Yes, sir. I mean, uh, HLS is basically the approach which one needs to follow because it is like uh, basically you write a C program to generate the hardware for FPGAs. Even I'm exploring that field, and it is like very interesting. So you need not know Verilog and all the low-level stuff. So if you know C programming, then you can write a very efficient code, and the tools basically take care of everything and generate very optimized hardware for that.
So why do you think that would be important, Aditya? Why don't you unmute your video?
So basically, most people here are, I think, familiar with C only, and Verilog and VHDL. Mostly people don't learn that well, and if we want to do something with the FPGAs and with chip designing, as you are saying, then it is important to know that there are tools which can take C code and they can like synthesize very optimized hardware for FPGAs. So that is also a possibility. Uh, yeah, other than that, I think, and the time consumption actually. Uh, if you write C code, then you can write that code very fast and in very short time, and you have all the libraries which are written by experts. That is not there in Verilog because mostly people don't prefer Verilog and VHDL. That is
Yeah.
it.
First of all, what it boils down to is that if I want to take an algorithm, like say a special video codec or some image processing module or something that you have in some small device that you want to build, right? And you find that the GPU is too fat and too heavy duty and too power guzzling a device on which to write this algorithm, right? So then you'd want to think of specialized hardware, and ideally you would first think of an FPGA. Okay.
Yeah.
Now to find a microelectronics guy who knows VHDL Verilog, first of all, is difficult because we turn out only about 200 of them in this entire country every year. Okay. Then the cost of actually designing, testing, implementation, validation would be very high. because it would take a lot of time, right?
Yes.
But if the same thing, you could get a software guy to do it in a few weeks for you, it would be cheaper and it would be easier to find a person to do it. So I think this is what's going to drive the future markets as these reconfigurable devices become cheaper and cheaper, and the tooling becomes more and more HLS oriented. There's a very compelling reason to be using software programmers to be doing hardware design, number one. But the sad thing is that the software programmers don't even know how to write decent software, leave alone hardware. Right? So first we have to teach software programmers to build tight and compact software, and then take them to the next level of using not only software engineering but hardware engineering principles to create really compact hardware code. But this whole area is very exciting, and I'm glad that you got a glimpse of the fact that it's pretty exciting. I'm sure some friends here in the audience would also have their own thoughts about this. I think Prashant from KJS has been intervening a bit here, right?
Yes, sir. Actually, just I found this idea very interesting. Just I wanted to ask, like, but like most of the work will go into design of compiler, because that would be like there would be interface between C and FPGA. So like most of the work will go into compiler design. Am I right?
Absolutely, absolutely. In fact, even as we speak, there's a lot of work already going on in compiler design, and we have a very big team at IIT Bombay which is working in the compiler space and especially the GCC space. There's a lot of optimization that you can do at the compiler level itself, and I think there's a lot of exciting stuff that needs to be done at this level. There's a very big movement in India itself also called Open FPGA amongst the FPGA community, the hardware community. There's a lot of work going on in the space in the area of open FPGAs, and I think there's a very strong need for an open source tooling which can take you from a high level programming language to the FPGA. Now, most of the tools at the moment are by companies like Synopsys and Xilinx and Intel, and they are proprietary and very expensive. Okay, so the whole process of designing FPGA cores and all that is quite expensive as a result of the tools being very expensive. But there's a strong movement now which is working on open source tooling, which is going to make this very cheap as we go along. Aditya, I don't see you. I'm going to hand the floor over to you now.
I just wanted to ask one question, sir.
Yeah.
Sir, so as an electronics and telecommunication engineer, what he
Yes.
or she must look into, whether he must look into high level C synthesis design, which is like right now getting momentum, or he also should put his mind into a compiler design.
I feel that both these things are important. Why should it be a he? It could be a she. I feel that she should be focusing on where the industry is going to be in 3 or 4 years' time. And I think this hardware, software co-synthesis is a very exciting area. So, and there's no escape from compilers. Whatever you do, is good to have compiler gyan, and it's good to have this FPGA gyan also. So why limit yourself saying that I'm an electronics engineer? You should just say a problem is a problem, it needs to be solved, and whatever bit of software engineering, computer science I need to know, I will learn. So this whole area in the boundary between computer science and electrical engineering is becoming very, very exciting at the moment. And this is a space where there are a lot of nice MTech projects to do and PhD projects and all that to do. PhD work.
Thank you, sir. Thank you very much, sir.
Okay.
Excuse me, sir.
Yeah.
Sir, I had a doubt. In the competition, which FPGA board will be using? It is a generic Intel or Xilinx board or a e-Yantra model of that?
No. We are using a off-the-shelf DE0 nano board, which Aditya can tell you a bit more about. So, as you know, in the competition, we have two stages. Stage one is done totally inside a simulator. So, if you look at it, it's more like a hardware MOOC, right? Everybody can do it. But in stage two, because we have to buy and give you the kits and they cost money, right? We select a certain number of people who've done well in stage one to give them the hardware in their hands at our cost. And this has been very exciting for us in the sense that as a result of this, we've been able to train large numbers of students in hardware design capabilities as a result of the competition. And Aditya has played a very important role in this theme last year and this year also.
For simulation, we are using Cortus.
Yes.
And for hardware, it is Intel based or e-Yantra. Means that board which you are telling, that is an
It's not an
e-Yantra.
e-Yantra board. It's off the shelf. Aditya will give you details about it.
Yeah, so that board, yeah, that board is from Intel, D0 Nano board. You can search for it online. It is basically a entry level FPGA board, which we will be using. And for simulation, we can use Cortex. And there is also one more simulator called Model Sun. So we'll be using both of them in this particular thing.
And a last doubt that in the competition, the language is a barrier that we have to use only VHDL or Verilog or whatever we are comfortable with, we can use that.
Actually, in the competition, we will be using Verilog because compared to VHDL, Verilog is simpler. Simpler as in it is easy to type and it is easy to read and easy to understand. So that is the reason why we will be using Verilog and not VHDL.
Can you tell me that board again? What board?
DE0 Nano.
DE0 Nano board made by Intel.
Yeah.
Okay. Thank you, sir.
Aditya, the floor is yours.
Yes, sir. Yeah, okay. So I'm done with my presentation. So if there are any more doubts, I can take them, or maybe maybe we can end if there are any. If there are
maybe
questions.
they can mail them to you also, no?
Yeah, they can mail their queries or they can mail them to support. I can take them and answer them.
So maybe Aditya, you can close by vote of thanks to the e-Yantra team behind the scenes, your colleagues.
Yeah, so thank you everyone involved in this particular session. So Vivek, Ajit sir, Kavi sir, you of course, then the entire eLSI team. There is Gargi also, I think, who is working behind the scenes. So everyone, and I hope that today's session was helpful to the audience. And yeah, as I said, you can mail your queries to us, and we'll be happy to solve.
Excuse me,
Yeah,
sir.
so yes.
For the competition, the theme is there. So a theme is to be selected by the team or to be selected by e-Yantra.
I think you are supposed to give your preference, and based on your preference and some criterias which we have, you will be given a theme.
So task 0 would not be common for everyone. The theme which we select will be moving in that direction.
Yeah. Task will be specific to your particular theme.
See, the theme which is allotted to you is based on your capabilities, your exposure, your background, what kind of hardware you have access to, and things like that. So we have a basis by which to allocate themes, and obviously we take your preference also into account. See, the main goal is that we want the competition to be a positive learning experience for you. So it requires a certain amount of background and a certain amount of resources. Like for instance, if it's a very simulation and ROS and gazebo intensive theme, is no point having a kludgy laptop and you get frustrated all the time and you can't do any simulation. So we do take the machines that you have into account, and we do take your background into account as to what kind of exposure you have. But I think in the sake of time, we should close here. I'd like to give a big hand to the team which has brought you a very nice talk on FPGAs, and join me in appreciating Aditya Gudla, Vivek, Ajit, Gargi, and the team in the background.
Yeah.
Thank you.
Yeah, thank you, sir.
All the best.
Thank you, sir, and thank you, Aditya, for the wonderful session. And before we close, we have a quiz for the participants for the session attendees. So the quiz will close in the next 10 minutes. So it's 12:34. It will close around 12:44 or 12:45, and you need to pass the quiz in order to get your attendance certificates. Okay. So thank you all once again for joining the session, and I would also thank all the participants that are present on the YouTube live. So thanks all for joining.